All right, today we're going to have lecture number 7, and today's major discussion topics are going to be sensors in general, just concepts of different types of sensors that we have, different types of ways that we can use sensors. So the first question to ask you is, and I'm looking for my notes. Did I put my notes up there somewhere, or did I leave them in my office?
I don't see him up here.
Oh, we're in bad shape. I'm going to have to go and fetch him then. All right, there's 3 major topics today. One is A to D converters. How many of you have actually covered A to D converters already? All right, half of you. Number 2 is going to be the concept of sonar, ultrasound. And number 3 is going to be the concept of wheel encoders. And for that matter, Hall effect sensors. Each one of these will have a concept where we'll need to stop the lecture for a little bit, and you'll have to turn to somebody and do a computation. All right? So, the first aspect of this for A to D conversion, analog to digital conversion. I want to find out who's available here to play a game of chance against me. All right, Mr. Hill, have you got a trip to the prize closet already?
No.
No? Okay, good. For a trip to the prize closet, I'm thinking of a number between 0 and 100.
8.
And I'm going to give you 8 guesses to get that number. However, when you give me a guess, I'll tell you higher or lower. So if by chance the number I came up with was 75 and you guessed 72, I would say higher.
Like, how much higher?
No, I'm not going to tell you how much. I'm just going to tell you higher or lower. I give you 8 chances to guess. Do you think you can get it in 8?
Sure.
I think so.
All right. So I will write down my number on this piece of paper here, just in case. All right, I got my number. I'm not going to show you. So, again, find number. Between 0 and 100. Give me your first guess.
50.
50.
This kid's smart.
It's higher. Oh, I'm sorry, hold, it's lower.
You might want to write your number down.
I was thinking of 72, which is not the choir 7, whatever I said before. All right, go ahead.
25.
25. It is higher. This is hard.
I got 6 guesses left, right?
Oh, you got 6 guesses though, yeah.
Have it again. Again.
40.
Higher.
Right, so you did 45.
So is it 46?
Yeah, I'm gonna go with 45.
Higher.
What? 46?
All right, now you guess.
Dang,
What's
okay.
your percentage?
There's only 4 numbers. 47. 47.
Higher.
48.
Higher.
Higher.
You should be like higher.
Higher. Yes. All right, let's see. 1, 2, 3,
7.
4, 5, 6, 7.
Okay.
Okay, you got
Highest
close.
closer.
I'm gonna make it a little bit harder. All right. Who's my next volunteer?
Christian.
Yeah, Christian?
Yeah, Christian wants to know.
You ready?
Sure.
All right, no. Find a number. Are you ready for this? Okay, sure. Okay. Find a number between 0 and.
Amelia.
You let me figure this out, right?
2 decimals.
255 in 8 guesses. Oh, let me just say, find a number between 0, 0, 0, 0, 0, 0, 0, 0, and 1, 1, 1, 1, 1, 1, 1, 1. In 8 guesses.
Shit.
You do realize that it's difficult for me to bleep out things.
What's the material?
My bad.
125.
Is that your final answer?
Said 8 guesses.
Is it?
Oh, I did it.
right.
My number.
Guessing
All right, let me come up with that. All right.
Good job.
Okay, I got my number.
Well, that's my number. 125.
135. It is lower.
75.
It is higher.
100.
It is higher.
120.
It is higher.
128. 28.
128. It is higher. You've got 3 left.
131.
131. It is lower.
That's a number.
In other words, you got lucky, as a matter of fact.
I got lucky.
Yeah.
I said 131.
Go ahead.
129.
Ding, 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 ding. All right, there you go. So, one thing I want to point out to you is this. Oh, what is this? Well, it's between, you thought base 10 as opposed to base 2. So what would be the accurate way of, or another way of doing this? Well, first of all, you can choose to split the distance exactly in half, but doing it digitally. So one thing you could do is you could say, all right, my first guess is 1000, 0000. By the way, that is 128 base 10. This is base 2. So I would say higher or lower? No, we already know it's 129, so it would be higher. So what's the next one to guess? Well, 11000000. Base 2. This is what value? I believe it's 192. And it's lower. So the next thing I need to do is 1010000. That's my next guess, which is 128 plus 32, which is 160, correct? And it's lower. So the next choice is 1, 0, 0,
1.
1, 0, 0, 0, 0. These two. And that is what value? 142? Is it 142 or 144, right?
44.
It's lower. Now, 1, 0, 0, 0, 1, 0, 0, 0.
136.
It's 136. Lower. 1, 0, 0, 0, 0, 1, 0, 0, base 2. This is
132.
132. Lower. 1, 0, 0, 0,
0, 0.
0, 0, 1, 0, base 2 is 130, which is base 10, will be lower. So obviously we know that it is so how many steps? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7.
So in both instances, it works better just to guess randomly.
But
No,
well, it's not always this way. When you split it exactly in half, you are definitely assured of getting it in 8, always. And in many cases, it will be 8. In some, it will be right on if it's a power of 2. And if it's an odd number, it'll always take 8. If it's an even number, it could be as short as 1. It could be as many as 7. Yes.
I don't understand that format.
You mean this right here?
Yeah.
It's binary.
You have never had binary numbers before?
I have.
Okay, that's a binary number.
Excellent.
I didn't do too well in the class.
Okay. You introduced. We could cover this in a little bit more detail offline.
Okay.
But all this is a binary number. It's base 2. So for each place,
2 to the 0.
this is 2 to the 0. Whoops. 2 to the 0. This is 2 to the 1. 2 to the 2.
2 to the 4.
2 to the 3. 2 to the 4th. 2 to the 5th. 2 to the 6th. 2 to the 7th. Which means that if we have the number bit there 1 in this position, 2 to the 4th is what value? So the equivalent of, in this case, 0, 0, 0, 0, 0, 1, 0, 0 is equal to 4 decimal. That's base 2.
Okay. I have to practice it, but that makes sense.
And we can look at practice later because this will actually come into effect when we talk about A to D conversion. So why did I do this game? By the way, both of you win, so you get to come up to a trip to the prize closet. And since the past trip to the prize closet, I have new swag.
Oh, snap.
So I've got more squishy balls.
You get the book that he doesn't want.
I've got additional man purses that they give away whenever you go to conferences. And I've got, let's see, there's something in there too that was interesting.
64 gigabyte flash drive.
A what? I don't think I want to hear that. No, never mind. All right, so why did I go through this?
A to D conversion.
A to D conversion because in our machine, what we want to do is read something in the external world and represent it digitally. And so we're going to see an example of that. It looks like maybe we need to do a little bit of backup and discussion of our of our digital numbers. So I'm going to give you a quick little assignment. This is 626. So your quick little assignment today is we have the value 7, 6 hex. The conversion of this to binary is 0111, 0110. So the value of this simply is going to be, well, that's 16, 32, and 64.
What's X represent?
0x mean it's going to be a hex number. So this just basically says what follows is a hex number.
Okay.
Base 2, so this is equivalent to decimal 64 plus decimal 32 plus decimal 16 plus decimal 4 plus decimal 2, which is equal to some number, which you'll do in our commercial break. All right. So your goal right now, let's practice this, is if I give you a hexadecimal number, hex 2A1, tell me what it is in base 2, tell me what it is in base 10. Also, if I give you the value 1001 in base 10, tell me what it is going to be in base 16, tell me what it's going to be in base 2. So, do these exercises. All right? I give you a few minutes and a break. All righty. We're gonna get back down. I'm gonna throw you to the wolves. All right. We're gonna
Wrong.
run. We're gonna let you go and do that for a trip to the prize closet. And what is the answer for any one of these two? You can choose the one that you're most comfortable with.
Oh, okay. So I'll do the whichever
No,
one.
not that one. This one or that one.
Alright. So
Hey, you good, dude.
right here.
Okay.
Okay. So I'll do this one. It's easy.
That one looks actually good.
Alright. So it's 1001, right? For the 10 digits. With like a base of 10. Alright. So 2 to the 9 is 512, and 2 to the 8 is 236, and 128 is 2 to the 7, and 2 to the 6, 2 to the 5th, and then if you add the 16, you're gonna exceed 1001. So I added 8, that's 1000, and then plus 1 at the end. That's 2 to 0.
Okay.
Yeah.
I'll live with that. So let's see what we have here. We have the answer to this in binary is 111110101. Everybody agree with that? And the easy thing is that once you've got that, this turns.
No, that's wrong. It's 1001.
1001.
The end just hexadecimal's wrong too.
Yeah, that's we got 5 ones in the beginning.
And then 1001.
No prize.
No, they 0 and then 1.
What?
5 zeros, 1 0 more.
Ah, so it's this and this.
Yeah.
Then I
Oh,
You
okay.
got 2 ones.
So this is the number 9 in hex. This is the number F in hex. This is the number 1
There you go.
in hex. So it's
You're missing a 0.
1.
That's wrong.
F9.
That's wrong too.
3
That's wrong. You're missing a
It's
0.
3 9.
3E9.
My
3
math is
E9.
right?
Yeah.
And what's wrong?
You're forgetting a zero in between the.
Yeah, right there.
That one.
No,
No, yeah.
Well, add another one to the
Then
left.
another one to the other side.
It's two.
Add another one to the left.
Just mark that out. Just mark out that whole number. Just add one in front.
It's 5101
There you go.
001.
1.
Oops, 1, 1.
1 1 1
One.
0
0.
1 1. No.
0.
0 1.
4.
What?
Yeah.
4.
Why you had 0 right there?
Because it's.
That's not looking at right,
Subtract
man.
32,
Just why
right?
just
Subtract
force.
the eight.
That's it. That's a
That's not
number.
fours. That's like 8.
That's a number.
Oh,
3E9 is the number, so it's 3E9.
My bad.
One way to tell is to look at the values. One of the big ones in digital that you can know about is 1024 decimal
That's good.
is 2 to the
10
10. That means you need
gigabyte.
how many bits to be 1024?
10. 11.
11.
That was a joke. I was just kidding.
That means 2 to the 10, with 10 bits, you could represent from 0 to 1023, which would be from 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, to 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, base 2. So you need a total of 10 bits to represent the number 1001 in decimal to be anything else. So this will turn out to be 3 E
3.
9. It's got to be 9 because it's an odd number, right? Do I even bother doing the next one? All right, the easiest way is convert this, first of all, into binary 1, 0. A is the pattern 1, 0, 1, 0 in binary, and then 0, 0, 0, 1. Only a few ones, so this is going to be equal to 512 plus 128 plus 32 plus 1. So that's equal to what? I don't want to
673.
6 what?
73.
673.
All right. I'm all proud of you. Did you get your trip to the prize closet?
You get some fruit.
That's wrong.
I think you forced me.
I'll let you do a trip to the prize closet at the end of class, all right?
Alright, thanks.
Well, I mean, you know, we put you through all that. At the very least, we could, like, you know.
Yeah.
That's back in sophomore year.
That's what, 7 years ago at least,
7
right?
years ago.
Right now.
Let's not make fun of my college career.
Dr. Conner, what else do you need? I want that coffee cup.
Well, it's funny you mention that because, let's see, how many of you have actually been through the graduation ceremony here so far? 2 of you,
I'm
right?
watching on YouTube.
Yeah, so, if you've seen it on YouTube, the chancellor has the same jokes every year. He'll say whether you're on the 4-year plan, the 5-year plan, the 6-year plan, or I don't know how long I've been here plan, we're proud of you. Sure. Okay, so let's go on. Now that we have a good analog to digital or a good binary background, let's talk a little bit about analog to digital. And, you know, things like why is it needed? If you think about the world today, pretty much everything that's worth measuring is an analog signal. It is temperature. And I don't know about you, but if I want to figure out what the temperature is, I don't immediately say, oh, why, it's 10110001 degrees out. and there's actually nothing in the world today that will give you a digital signal immediately based on what the temperature is. Everything has to be converted from its analog instance into a digital representation. Same thing with voltage. Yes, voltage is in many cases 0 and 1, logical, right? But if you're looking for a specific voltage level, anywhere between your maximum VCC and 0, it's going to be some sort of analog signal because it is something that you measure that is going to be in a full range. So, anything from temperature, thermometers, thermostats, car engine controllers. Think about all of those applications of temperature for embedded systems to read. Light. Digital cameras need to know how to adjust for any signal that comes in. Remote control, tanning bed, UV monitor. Rotary position, wind gauge knobs, but it also has to do with wheels. Pressure, think of all the applications in the world that we have pressure. Acceleration, one thing that's not even in there is, for example, football helmets. Some of them are now instrumented with accelerometers just to see how much people or football players are actually getting beat up when they play, or to see if they are available or if they're going to have a concussion, and then other types of inputs. So these are continuous signals that need to be converted to a digital form. So we're going to have all sorts of devices, and usually these devices you're measuring voltage. Sometimes you measure resistance, but you can just give it a voltage and it'll tell you what the resistance is. The big picture is you have a sensor like a pressure sensor. You feed it directly into an analog to digital converter. They come in separate chips, or it could be on the actual microprocessor, microcontroller that you have. Then with the code, you write software which will then say, okay, let me read. This is an example of A to D port 0. Read the port, put it into a variable, work with it. My voltage reference is going to be 1023. In other words, we're going to look at precision associated with A to D conversions, and then how you do all the calculations. There is, for every sensor that you have, there is going to be some sort of curve that's going to tell you what your typical measurement is going to be. So, for example, depends on what your pressure is, and this is kPa, was it kPascals, right? Kilopascals. It will say you will measure 2 volts if the kilopascals is approximately 100 based on a maximum possible temperature. So there will be some variance depending on what the temperature is of the actual measurement device. Because in most cases, it's still silicon or some sort of manifestation of silicon that's going to be doing some measurement. Sometimes it's also associated with silicon with small springs inside and some other doped type of material. CO2 sensors have a different type of material that can detect what it is. So a person who is doing A to D conversion will have to have a table of how that particular sensor works. So, getting from analog to digital, we're going to get into some electrical concepts that I know you mechanicals had in ECGR 2161, if you could remember that far. Comparator. You take these two, if they're the same, you'll have a 1. If they're different, you'll have a 0. And that's all we're doing. We're putting a whole bunch of these together. But typically with an A to D converter, what you'll have is a reference. That's the most voltage that you're going to measure. This is the actual measurement of what you're going to do. Most A to D converters, you're looking at going from 0 volts to some upper reference. So let's say I have 8 volts, 0 to 8 volts. So if I have a measurement here, let's say 0 to 7 volts, I'll even make it easier. 0 to 7 volts. So at this point, if I had 0 to 7 volts, if my input here that I'm going to measure is 0, it would be at the low end. So this would be 0, 0, 0, 0. If I measure 7 volts, it's at the high end. So this would be 1, 1, 1, 1. Oops, nope. I should say 0 to 15 volts. All right, that makes it better. 0 to 15 volts. If I have 0 volts, it's 0, 0, 0, 0. If I have 15 volts, then it's 1, 1, 1, 1.
Yeah.
I'm going to go into, in a second, a little bit more detail about how we're going to do that. But then there's another concept associated with this of sampling. Now remember, this is a continuous number that you're going to, or continuous value that you're going to have to quantize. You have to find the quantity of. And typically it's a signal that's continually changing. And so if you're converting it to the digital world, you actually have to sample it at a certain frequency. So in the earlier slide, I showed here something called a clock. And that's because the clock is used to say, all right, at this time measure, now this time measure, now this time measure, now this time measure. So it's going to be continually changing in most cases. In some cases, it's not going to change much. If you're using, or if you're trying to make this into an oscilloscope, let's say, and have a certain frequency, yeah, that signal's going to be changing. If you're measuring temperature, I don't think the temperature right now is going to be different at all in the next 5 seconds. And then the next 5 seconds after that. So it's an ever-changing, very slow-changing measurement. So in our waveform, you're going to sample every delta t, whatever t is determined. Sometimes you don't have to sample that much, as in the example of the temperature. Sometimes you do, as in the example of an accelerometer for an airbag, to see if your car is in an accident. So we will convert some sort of value into as close as we can, the closest number we can get to. Because remember, this is a continuous signal, and in the digital world, we're really limited to what we can measure. In this previous example, remember I said 0 volts to 15 volts. What if the voltage is 7.5? We're going to have to get close, but it's not going to be exactly 7.5 because the resolution is such that it's going to be observed as either 7 or 8. So the more resolution you have, of course, the closer you can get to it. So let's see just how close you can get to it. So we're going to have a function that is going to be associated with, depending on what your voltage is, what your output will represent. So in this case, we have a voltage from 0 to 4 volts. And at 0, it's going to be 0, 0. At 0, 1, it's going to represent 1 volt. At 1, 0, it's going to represent 2 volts. And at 1, 1, it's going to represent 3 volts. So it looks like 4 volts is even difficult to get in that, right? The more and more bits that you have associated with it, the better resolution you have, and the closer you're going to come to what the actual value is. So let's take a look at some concepts. I'm not going to go into so much detail on this, but we could look at some of the examples. This is the general equation associated with A to D, and I can assure you that this is going to show up on a test. So these notes will be online. You can take a look at this, but we're going to go through a couple of examples. Oh, in fact, here we have one right here. Let's say we have our represented converted code, it says. Converted code just means that our digital value that's going to come out is going to be something. Our plus reference tells me what the maximum voltage is for our A to D converter. Vin is what we're actually measuring. And this tells me how many bits we're able to represent this. So I have the following situation. I have an A to D converter that has 10 bits. This is really hard to do with a mouse. So my A to D converter has 10 bits, and I can measure from 0 to 5 volts. And it just so happens that when I'm recording this measurement, it's going to be 3.3 volts. So with my formula, by the way, this handles our rounding, because you combine this plus 1/2 with this function, which is take the floor, which basically is the equivalent of rounding. And we do the formula. Well, if our measurement was 3.3 volts, we're representing 10 bits. Our digital value will be 10 bits. The maximum value that our range is 0 to 5 volts. Then the digital number that will come out is 676 base 10. What is the value for this in hex or in binary? Well, I just so happen to know that it is going to be 1 0 1 0 1 0. And now I got to do my additional math. Add 5 onto that. 0 1 1 0. And I got that because one of our previous problems, we had 673, right? So, using this concept, let's take another example. And remember this formula right here, and I'll clear it up so it's easy to see. Remembering this formula right here, let's say that we have, again, 10 bits. And my measured voltage is 0.5 volts. Now, is my end answer here going to be fairly big or fairly small?
Small.
It's going to be fairly small, right? Because you're getting really close to the 0 volt setting. So let's do the formula. And I'm not smart enough to do it with the, what do you call this thing? Mouse. So we have, in our example, our number is going to be equal to, what did we say our formula was?
Vn.
Vn
Minus
Vref.
times
to the 10
to the big N
Plus the
over Vref
plus 1/2.
plus 1/2, and take the floor of that. So in our example, it's 0.5 volts times 1024 over 5. Oh, I didn't say what the bottom voltage is. It's 5. Plus 1/2, taking the floor of that, which is 102.9. Take the floor, which is equal to 102. That's because I had 0.1 up here and 1 down there, and I was able to just move the decimal point over. As another example, let's say our N is equal to 8 bits. Our range is from 0 to 3.3 volts. And the voltage that we read is going to be 3.0 is equal to our Vin. What is going to be our N? Our N is going to be equal to 3.0 volts times 2 to the 8 over 3.3 volts plus 1/2. Take the floor of that. I didn't bring my handy dandy calculator with me. Oh, I can go to this one. So again, I had, it's funny, I can't turn the screen on its side to get the scientific one.
You tried it?
Oh yeah, let me try.
Space 2.
We said 3 times 2 to the 8th is what value? 256. I'm going to divide by 3.3 equals, I'm going to add 1/2. That's 233.2. Or 233. What would be the max that we could have there? What would be the max value if you have 8 bits to represent it? Right? Remember, the max would be 256. So does that look about right? Yeah, because it's pretty, 233 is pretty big, 3 volts is pretty darn close to 3.3.
Yeah.
Question? Yes?
So the N we're getting is just converting it into the base 10?
Yeah, the base 10. If we were to look at what's the representation of that in the computer itself, then the value would be what? I know that's going to be 1.
Oh, we can't see that.
We're at the base 2.
Plus 64. Yeah, I'm sure the next one is 64. Anybody do this math for me? I'm too lazy. Yeah, here.
You got babies there.
There we go.
Oh, come on, Dr. Conrad.
What?
Wait a minute. Is that on? We could have. Oh.
Yeah, isn't that neat? The binary calculator. They'll even turn it into hex for you if you want.
Don't you wish you knew that when you're going through that
What was
class?
the answer?
I wish I knew that doing the problems.
Well, you know, you gotta learn it one way or the other.
What was the answer?
All right, it was E9, right there. E9.
Oh.
So, now, as always, let's do something, turn to your neighbor and do the following. So let's say, oh, we got plenty of time for class yet. Let's say you have a 12-bit ADC. You're measuring from 0 to 12 volts with your ADC. You have measured Vin is equal to 7.55 volts. So what is your N? Represented in decimal and binary and in hex.
What about BCD? Come on. That's curveball.
Who asked for BCD?
Huh?
You?
right here.
I got it.
All right, decimal, binary, hex. You have to do it in BCD as well, and
Octo.
all right.
Make it do octo.
All right, so let's pause the recording and spend a few minutes solving this this problem.
It's a bribe.
All right. You know what? I can still edit that out. All right, so back we go. You guys are gonna make me all flustered and stuff. The answer. Do you want me to just solve this, or does somebody want to come up and do it?
We believe in you.
You can make it. You don't want to work with me in research.
We think you're good enough.
All right. So
Come on, man.
n is equal to v in times 2 to the n over v plus ref plus 1/2. Oops.
So that will be 2576.
Is that is equal to
2576.
7.55 times 2 to the 12th over 12 volts plus 1/2. Because I'm lazy, I'm going to do this again.
2577.
I'm going to do it anyhow because people in 2 raised, where to go? The 12th times
7.55.
7.55 divided by 12 equals, we're going to add 0.5 equals, so it's going to be 2, 5, 7, 7.6, 2577, and of course when we convert it into binary it's going to be, or hex, might as well just do hex, it's easy. A11, binary is 1010, 0001, 0001. By the way, a 12-bit A to D converter is pretty typical for one that will stand alone. And some of the higher-end microcontrollers have a 12-bit A to D converter inside. A typical run-of-the-mill, inexpensive microcontroller will have typically either 8 or 10 bits of resolution. All right, yes?
When you're doing the bit coding, do you work from left to right to figure it out?
Or do I just type it into my calculator? There are different ways to determine. You could divide the number by repeated powers of 2, or by repeatedly by 2, and it gets you bits. There's a couple of ways to do that. For what you need in this class, you can use a calculator.
Okay.
Yes?
If I have the reading from like 40 to 20 milliamps, can I use the same equation? Instead of using V ref, I can use I ref, say 20 minus 4.
Say it again. If I want to measure a really, really small amount of current?
No. Instead of we have voltage from 0 to 5 volt or something, if I have something reading out 40 to 20 milliamps, can I use the same equation?
Well, don't forget what we're doing is we're measuring voltage, not current. And so if you're measuring voltage, if you're measuring current, what will actually happen is that your current measuring device will convert it into a voltage, which then the ADD converter can assess. All right? Now, one thing I should mention, and let's see if it's in my notes. Oh, I've already gone through a couple of these examples, so we looked at that already. You know what? I'm not going to go into great detail about what's in the inner guts of this, because otherwise you'll think it's on the test. One thing I should tell you is that the way most microcontrollers do it is similar to what we've already done, what's called successive approximation. You guess halfway, higher or lower. Then you do the next one higher or lower, 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 and eventually you'll get the actual example. Inside the microcontroller, this is what you'll typically see, a device that does successive approximation with an A to D or with a D to A converter. You don't need to see that. I don't know how much in detail I'm going to do all that. Pardon me?
Just reading the night quiz.
I'm going to do this. So, one thing that is important is that there is a concept called the Nyquist criterion, in which it says if you really want to measure something that's periodic, you need to sample at least twice of what the frequency of what you're trying to measure. So for example, if you are trying to measure a signal that looks like this, there we go.
With the triangles?
I never used that.
I don't either.
Does anybody know what this is?
Sine.
Yeah, good. We've taught you something in the years here, right?
Squiggle.
It's a squiggle. Very good.
Just
All right.
turn sideways.
So at this point here, it's about the same value as this point here.
Puerto Rico.
At the same value as this point here. Same value as this point here. So this is considered, what's the name for the time between here and here?
Period.
1 period.
1 period. So if my frequency is 1 period, obviously my measurement is going to be what?
Double that.
A line. However, there's a possibility that if you measure exactly 1/2 of the period, you can get this point, and 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 this point, which is a spaceship. Very good. Still a line.
Oh, I said phase shift.
Oh, a phase shift. Oh, I thought you said a spaceship. And I'm very glad you didn't say spaceship and were very serious about it. You get a single line. Also, it depends on where you are. You can also alias something. If you're at this point here, then you're at this point here, then you're at this point here. It actually looks like you're at a different frequency as well. So that's why it's good to, as we said in the slides, you want to be a sampling frequency which is greater than 1/2 of, or I should say less than 1/2 of the period of what you're trying to measure. And nothing says that you can't have it a lot more frequently than that too. So in the case of our temperature here, obviously you want to measure at twice of the frequency of the change of our temperature. And our temperature changes what? About once a day, all right? So you can measure it once an hour, once every 30 minutes, it's good enough. However, if you're looking at something like an accelerometer, which is measuring the frequency of some vibration, the vibration is at 2 kilohertz, you'll probably want to measure at what frequency? 4. More frequently than 4 kilohertz, right?
Or more.
I don't want to go into this.
Multiplex.
Send it there.
I will do this. When you are measuring all sorts of analog signals, typically you have a lot of analog signals that you want to measure. For example, if you have, let's take a good example that you're going to see in the next few days. Let's say you have a vehicle, and your vehicle is a Danny robot. You know, here's your wheel in the back, here's your wheel on the side. And on the front of your Danny vehicle is going to be a light sensor. This light sensor will send a signal down to the ground and expect a reflection back. And based on the value of that reflection, you'll get a different voltage. Well, you've got two of these. You've got one here and you've got one here. So you'll have two single sensors that will go in, and typically your hardware only has one A to D converter. So what you'll do, or what the processor will do, is it will take time. It'll measure one, then the next, then one, then the next, then one, then the next. It's able to identify, I'll take this device first, measure it, next one, and then you could use that data in your LabVIEW programs for your Danny robot. You have already seen examples of that in your, what do you call that little NXT, the Lego Mindstorm box, right? Some of you had a light sensor and an ultrasound sensor. And even though it had one processor in it, and it likely had only one A to D converter, it was able to detect the different devices by saying, now I give you time, now I give you time. Also, we typically put additional electronic hardware on it to protect the signal so that you get a nice clean signal that's not noisy as it's measuring. But there's another way you can do this, and that is to do what we call a sample and hold. So as we're measuring our device up there, let's say our analog input signal is there, every so often we'll flick a switch and charge a capacitor and then take it off, and then the capacitor will hold the voltage of whatever was measured. And so remember that periodic measure, wait a little bit of time, measure, wait a little bit of time, measure, wait a little bit of time. We do that by putting the sampling switch and charging or discharging the capacitor, because after it's been sampled, then it will discharge the capacitor and go in for the next sample. And that's what we have a sample and hold device will do for us. Some other stuff that we don't need to cover. I think I've already covered this. Why is this here again?
Digital to analog?
Oh, this is digital to analog. In our case, very often we have a microcontroller that will have a certain value that we want to output a certain voltage between 0 and wherever our Vref is. So if we had, again, 0 to 15 volts, and this is our output, this is the lowest bit, so this would be the value of 5. The output voltage would be 5 volts. Yes, sir?
So would this be like if you had a MyDAC and you had a voltage going into that and then it went into the computer and then it gave a voltage back out?
Correct.
Okay.
Where would you want to do something like this? Any application where you need to output a voltage that is varying between 0 and whatever you need. 0 and 5, 0 and 3.3. Pretty typical for embedded systems. So, I want to talk about our next lab coming up and how you're going to need to handle this. So, as I mentioned before, you're going to have a Dandy robot. And if you look at the robot itself, with its front wheels and a back wheel, we're going to have a detector out here, which will, the objective of that detector is to send a light, infrared light signal down and measure the reflection back. Now, what is the reflection, or what is the voltage? Well, you will have a signal like this that at a certain distance and this is about 2 inches, let's say, and let's say this is about 4 inches. You will have a certain peak voltage here at 2 volts. So what's the one thing you notice? This is a sensor right here. Will give you a peak voltage at 2 inches. What does that tell you if you were to measure, let's say, VB? You could be at either 1 inch, or you could be at what looks to be about 5 or 5.5 inches, right? So what would that tell you when you're deploying this certain, it's a sharp, and I'm going to have to look up the number for this in particular, it's a sharp IR sensor.
What's that distance again?
What is this distance here? I'm just saying in general. This is the distance. If you were to say, Mr. Computer, I have measured voltage A. And by the way, when you feed the sensor, I think the sensor, you feed it 5 volts. There's also a ground, and then there's a signal. So the sensor itself has 5 and 0, and maybe this up here is, because you usually don't get anything out of the sensor that is exactly 5 volts. Usually this is something like 4.8, let's say. And let's say this is 2.4 volts. So this would tell you what, if you have a point here and here, based on your curve. That says if you measure 2.4 volts, either the sensor is detecting something 1 inch away or 5.5 inches away. What does that tell you about the design of your robot?
It's not that accurate.
What does that tell you about the design of this sensor here if our objective is to see how far away the floor is?
Shows you your range.
Fail.
It should be arranged such that,
It won't
X
be
between
2
1 and
points
5.5
and
inches.
all right, say I got 2 people, so let's start with you, go ahead.
It'll detect the floor between a range of 1 inch and 5.5 inches.
All right, let's try your idea.
2 points should never have the same.
All right, 2 points should never happen in the same place, right? So what does that say about how you can physically mount this sensor right here?
Give it like a
At least 2
maximum of
inches.
2 inches or something.
At least 2 inches, right? And in fact, it'd be better to be a little bit more than 2 inches, right? So that you always know that you will always reflect off the floor there. Of course, if you run over something, it's going to be less than that, right? Or if the whole idea of this is to be a edge detector so that you don't roll down a stairs like in the Roomba, right? You don't want the Roomba to roll down the stairs when it comes to the edge of a floor or comes to the stairs. So you would say, I'm going to mount that sensor 2 inches above the floor, and anytime I get a voltage that is, oh, let's say some threshold there and below, that means that something's going wrong and I better watch out. Especially if you go from, you know, measuring 4.6 or 4.8, 4.8, 4.8, 4.8, whoa, 0.5 volts. What will that tell you? You hit a cliff, right? So the whole idea of how you build your robotic systems using these sensors is you use the concepts of the design of design of your voltage signal to be able to do whatever that device is intended to do. In this case, it's an edge detector. Yes, sir.
So will we should be able to like make a simple program just to test the sensor, and if we have like a piece of something and move it close, we can graph that voltage.
Exactly.
Okay.
So the question, if it wasn't picked up, is technically you can take one of these sensors and by moving a piece of paper closer and closer to the sensor, you should be able to replicate that curve. So for lab number 4, which is going to be assigned on Thursday, actually I think I'm going to post the information on it, you will soon, you will need to, using the tutorial help, you will need to ensure that your robot runs around and does not go off a table or go down a stairs. And by the way, if your robot goes off a stair, you immediately get an F for the class.
Just put cushion.
Because again, these robots are about $2,000.
Okay, just put cushion underneath.
What if it's pushed?
Just put cushion.
What if you put a cushion there?
Yeah,
I
it
don't
won't
think
break,
that
so you don't get an F.
Okay, if you use a cushion, you'll get a D.
I can live with that.
Oh, it's always somebody. All right, so the next discussion is going to be, since we didn't really get much beyond where I had hoped we would get, we will talk about sonar, ultrasound, and wheel encoders, and I may actually push off, I think I will push off homework 3 to the next Tuesday after that, because I want to talk about a few more concepts. But that's it, and that's it.